All right, Pirates, welcome back to another fun session of notes. Today we're going to be talking about classifying, which means determining what type of chemical reaction you have. So classifying types of chemical reactions. We're going to go through 5 of them, and we're going to take them one at a time. I'm going to give you a very simple breakdown of that type of reaction, and then a couple of examples of each type. Okay, the first type is the synthesis reaction. Synthesis reaction. Okay. In the synthesis reaction, well, let's break down that word synthesis. Syn means together. Thesis has to do with the process of creating. So what you're doing is we are bringing things together to make something new. So what we're going to do is we are going to take 2 or more things and combine them So we are making something new. We're taking 2 individual components and we are turning them into one thing. So typically what you will see, although not always, you'll see some sort of element and some sort of element. And you end up combining those to make a compound. Okay, so if I were to give you a generic example, let's say we have element A, there is no element A in the periodic table, and then element B, and there is a B in the periodic table, but we're not talking about boron. These are just substitutions for generic elements. If I took those 2 things and I put them together, I would get a compound which would have both A and B in it. Now, one thing to notice is that sometimes in some synthesis reactions, you might actually have more than 2, but the main thing to know in a synthesis reaction when you're classifying these things is you're always going to end up with only one thing. So at the end, you're only ending up with one thing. You're combining everything together, everything there together. So a dead giveaway that you have a synthesis reaction is that you end up with just one product. There's only one product available. There's lots of different examples of synthesis reactions. For example, if I take sodium, which is an element, and I combine it with another element, chlorine. Remember, chlorine is diatomic, so there's 2 chlorines for every molecule of the element. And we put those together, sodium chloride is generated, NaCl. Now I will quickly balance them, but I won't always balance them later on. Add the coefficients and you end up with some sort of synthesis reaction, right? I take an element, sodium, add it to another element, which is chlorine, and I end up with the compound sodium chloride. So that's a synthesis reaction. Okay, that's reaction number 1. Reaction number 2 is the exact opposite of a synthesis reaction. All right, that is decomposition. Okay, D means to undo or to get rid of, and composition means to be made of, so it's getting rid of what it's made of. When your food decomposes or when a deceased organism decomposes, right, it breaks down into its individual components. It breaks down into smaller and smaller molecules. So decomposition literally means to break down. And that is what we are going to be doing in a decomposition reaction. Once again, it is the exact opposite of the synthesis reaction in that you will always start off with only one reagent or reactant. You will only have one thing that you're starting off with. So in this case, going back to my example previously where we have A, and then we add A plus B to give you AB, we're going to start off with that compound. We're starting off with only one thing, and then we end up breaking it down into its individual components. Breaking it down into its individual components. So in this case, we have AB breaking down into A plus B. Okay, now typically most of the time, although not always on your examples, you are going to have a compound to begin with, just one single compound. And it's going to break down into its individual elements. Yep, element plus element. Now, it won't always be an element plus an element when you're just classifying. There's one or two examples on the quizzes and one or two examples on the practice worksheets where you end up with a compound as the product. But the main thing is that you are always only starting with one thing. So if you have one reagent and only one reagent, that's a good chance it's a decomposition reaction. All right, so an example of a decomposition reaction is going to be the electrolysis of water. So I'll take water, which is H2O, okay? And if I add an electric current to water at high enough energy, you end up breaking down water into its individual components, which is H2 and O2, both being diatomic atoms. And then, of course, I can always go back and balance my equation like so, and now I have my decomposition reaction. I start off with one compound with one thing and one thing only, and I end up with two things at the very end. You could actually end up with more than two things as your products, but if you're starting off with one thing and you're ending up with a lot more things, it is always a decomposition reaction. So the first two are exact opposites of each other. In a synthesis reaction, you have two or more things combining to make one thing. And then in a decomposition, you are starting with one thing and you're breaking it down into its individual components. Okay. The third type of reaction that we're going to be talking about is a single replacement reaction. Now, typically, to save some time for you guys, we'll often abbreviate that as an SR. It's not a true abbreviation for it, but for our worksheets, that's good enough. A single replacement reaction is always going to be the following way. You're always going to start off with one element, and you're going to add that element to a compound, and you're going to end up with an element and a compound. And of course, I'm running out of room, so let me use my scissors here, and I will resize it for you. Boom, and boom. So it's always going to be that type of formula. And so what I always call this is kind of like the breakup or the dump. So I'll show you what I mean in a second. So you start off with one element. Let's say I have element A, okay? And I end up adding to that element a compound, such as we'll go B and C. So I have compound A and then B and C. What ends up happening is in this reaction, one of the elements in the compound gets rejected, gets broken up with, and becomes single again at the end. So what we end up having is this A, let's say, if it's a metal, it's going to kick out the metal in the compound. If it's a non-metal, it's going to kick out the non-metal in the compound, and it's going to replace it. So it's a single or element replacement, and so what you end up getting at the end is you get one element by itself, in this case B, right? And we add to that the A that we originally had, and then the C. So there's different levels of reactivity of certain compounds, and so the elements and compounds always want to be with the one that will be the most reactive and end up being the most stable relationship at the very end. And so you have the breakup here, okay? So what ends up happening, you have one element replacing another element. There's always somebody single at the beginning, and there's always somebody single at the end. If you look at it like a relationship, there's always somebody single at the beginning and always somebody single at the end. So some examples of single relationships or single replacement reactions. We can have, for example, sodium. We're going to add sodium. Actually, we'll go with lithium. I want it to be a reaction that might actually occur. So we have lithium, and we're adding lithium to sodium chloride. And what ends up happening is, because lithium is a metal, it is going to replace the metal inside of the ionic compound. So lithium is going to swap that metal out, and you end up getting sodium by itself, and then you end up with the ionic compound, which is lithium chloride. So single replacement, you have somebody single at the beginning, lithium, you have somebody single at the end, which is sodium. Now, another example of a single replacement, you can have nonmetals doing single replacements. So for example, I can start off with sodium chloride, and I can add to sodium chloride fluorine. Okay, and I end up then, fluorine is a nonmetal, so it is going to, fluorine is a nonmetal, so it's going to end up kicking out the nonmetal in the compound. Element plus compound gives you element plus compound. So the fluorine is going to replace the chlorine, and you end up with sodium and fluorine now going together, and you end up with chlorine by itself. Now notice that chlorine and fluorine are both diatomics, so even though they are elements, the element is by itself, but there are two of those elements. And then of course at the very end, you can always go back through and double check that you have things balanced, like so. All right, so that's a single replacement. In a single replacement, a metal is replacing a metal in a compound, or a nonmetal is replacing a nonmetal in a compound. A single thing, or an element, is replacing another single thing, or an element. All right, the next type of reaction is called a double replacement. Okay, we like to call this the swapping partners, the wife swap, whatever, double replacement. What you're doing is the ions in two compounds switch partners. Oops, I can't spell today. Switch partners. Okay, so in this example, what you're going to get is you're going to get a compound plus a compound. Okay, compound plus a compound. I'm going to use my scissors, make this smaller so it fits. In fact, while it's scissored, I can copy it and paste it. And so if you have a compound and a compound being added together, and you end up with two compounds at the end, that is a double replacement. Using generic terms, not real elements, once again, I would have A combining with the nonmetal B, and then I would add to that compound, compound C and compound, trying to use different colors so you can see the switching happen a little bit better. All right, and so what ends up happening is the metal in one compound is going to switch places with the metal in the other compound, or the nonmetals are going to switch places either way. But you have doubles on both sides, you have partners on both sides, you have two compounds on both sides, and so what you end up getting, the C now ends up going with the nonmetal B, because it switched with the A, and then the A ends up going with the D. So they're switching partners, double replacement, the wife swap. All right, and so you're switching those partners there, you're recombining with those things. And so an example of this could be, we could have, for example, lithium chloride, and we can combine that lithium chloride with sodium, we'll say sulfate. Right, those are both compounds, and so in this type of reaction, you would end up having them switching, and you would have the, copy this over, boom, paste it down there, copy this over, and paste it down there. And so what you would end up having is you would have the lithium now ending up with the sulfate. We got these balancing rules, so I'm going to bring that 2 over with it. Trying to save time, but of course ends up being longer. All right, undo, try it again. So I had the lithium sulfate, and then I end up having the sodium going with the chlorine. Sodium going with the chlorine. And so you end up with 2 compounds on one side, 2 compounds on the other side. So double replacement and single replacement, you both have partner switching. And a double replacement, you have doubles or compounds on both sides. And a single replacement, you're always going to have an element plus a compound, gives you an element plus a compound. Okay. The last type of reaction is going to be called a combustion reaction. Okay? Now, there's the true definition of a combustion reaction, and then there's also the definition we are going to be using in this class. The definition we use in this class is just a subset of combustion reactions. Technically, I'll tell you what a combustion reaction should be. A combustion reaction is where you have oxygen combining with every other element on the reactant side combined with every other reactant on an reaction side. Now, in ours, what we're going to do is we're going to do a narrow definition of combustion reaction, and that's going to be oxygen combines with a hydrocarbon. Okay, what a hydrocarbon is a compound that contains hydrogen, and so we have hydrogen, let's say we have Y number of hydrogens, and carbon, so it contains carbon as well. Typically, we put carbon first, so I'm going to put carbon first here. So we have X number of carbons, we have Y number of hydrogens. Sometimes you also have an oxygen, so I'm going to put an oxygen in there sometimes. But it's only the carbon and the hydrogen that are important, and I'll show you why in a second. So what ends up happening is we have our C, X, H, Y, and then sometimes our oxygen, and I'll put Z for oxygen, and we're going to add to that oxygen, because oxygen is going to combine with everything. Okay, so the oxygen is going to combine with the carbon. When oxygen combines with carbon, the most common and stable compound is carbon dioxide. Okay, then the oxygen is going to combine with the hydrogen, and when the oxygen combines with the hydrogen, you get the most prevalent compound on the earth, which is water. It's the most stable version of hydrogen and oxygen. And so a dead giveaway for a combustion reaction is that you have carbon dioxide and water as your only two products. Okay, and oxygen is one of your reagents. Okay, so when you do this, you end up having carbon dioxide and hydrogen as your products, oxygen as your reactant. And so some examples of this, those of you that took a biology, which should have been all of you, you've seen the chemical equation for cellular respiration. Cellular respiration is a combustion reaction, right? Cellular respiration is a combustion reaction. In this reaction, and I can balance this one because I've memorized it. So we have 6 of these oxygens, 6 of the carbons, and 6 of the hydrogens, and there we go. But notice the products here are carbon dioxide and water, and our reactant is a hydrocarbon plus oxygen. This is also the same chemical equation that you get when you burn any organic material. You have the oxygen combining with everything. One more thing I forgot to say is that when oxygen combines with itself, it just makes more oxygen, so it makes things burn a little bit faster. All right, and so this is what happens in the engine of your car. Most of the material that comes out of the gas pipe is carbon dioxide with a little bit of carbon monoxide. And if you ever looked at a car's tailpipe after it's been driving a while, you will notice some liquid droppings coming out, and that is that water. And so carbon dioxide and water are coming out of your tailpipe, and you're burning a hydrocarbon, which is fuel that is high in different octanes and nonanes and decanes, different hydrocarbon chains, different carbon and hydrogens amounts. You can also burn something like methanol or ethanol. Methanol is also known as carbon tetrahydride, methyl alcohol. Methanol is also known as methyl alcohol. It's what happens when you have carbon with 3 hydrogens and then 1 hydroxide, and you add oxygen to that. And then once again, when you burn that methanol, you end up getting carbon dioxide and water. Obviously, you should balance the equations, although notice that these balancing are a little bit more complicated than some of the earlier ones, and so I'm not going to spend a lot of time going over that. But a big giveaway that this is a combustion reaction is that you have carbon dioxide and water and oxygen as a reagent. So the 5 types of chemical reactions, and we're going to give you lists of these, are going to be a synthesis reaction in which you have 2 elements or 2 things and they combine into one thing. The dead giveaway of the synthesis reaction is that you end up with only one item in your reagents, only one, or in your products, only one type of compound at the end. Decomposition is the exact opposite. You only have one reagent and it's breaking down into multiple things, usually elements, although not always. In a single replacement, it's kind of like the dumping, like one couple is together and it dumps one of them for somebody else. And so you always have somebody single at the beginning and the end. Metals replace metals, nonmetals replace nonmetals. And you always will have an element and a compound on each side of a single replacement. A double replacement, by the way, I forgot to mention, double replacement we will often abbreviate as DR. Okay, in that you have 2 compounds on both sides, so a compound and a compound gives you a compound and a compound. You end up switching. The nonmetals either switch or the metals either switch, but only one thing is switching. Because if both switched, then they end up back with their own partners. So typically what I do is I only switch around the metals. And so in this case, you have lithium chloride plus sodium sulfate, giving you lithium sulfate and sodium chloride. And then the last one is oxygen combining with every other element on the reactant side. Typically will show you oxygen combining with a hydrocarbon. And when you do that, you end up with carbon dioxide and water. All right, I hope this helps. Let us know if you have any questions, let your teacher know, or sign up for an academic support session or a tutoring session, depending on what year this is happening. And then I hope you have a great day, Pirates, and I'll see you later.